We turn to describe the double-sparsity dictionary learning algorithm, which fights some of the difficulties that regular methods encounter. This work was done by Ron Rubinstein, Michael Cibulewski, and myself. Let's start by presenting its core idea. We are interested to train the dictionary D, and we will impose a very specific structure on it. D should be equal to D0 times a sparse matrix Z. In this relation, D0 is a fixed matrix that represents a fast transform of some sort, and Z is the true unknown which defines the overall dictionary D. This matrix will have sparse columns with up to k1 non-zeros in each. Where is this idea coming from? What is the rationale behind this decomposition? Well, in this structure, we essentially believe that each of the atoms in D is in fact a sparse combination of atoms from D0. Does this make sense? The answer is yes. Here is, for example, a dictionary that we got when training on the image Barbara. Observe that the atoms are texture images of various shapes and orientations. These could be created by sparsely combining atoms from the 2D DCT dictionary shown here. So the double sparsity idea relies on the fact that our atoms are themselves sparse combination of fundamental atoms taken from a transform. Why is this structure so appealing? The first observation we make is that multiplying by D or its transpose as required in pursuit can be done fast, because multiplying by D0 is fast and multiplying by a sparse matrix is also fast. Another benefit in this approach is the massive reduction in the degrees of freedom that define the learned dictionary. This suggests that we may do well with less examples or get to a better final result. A third benefit is the ability now to grow the dimensions of the signals to be treated, since storing or working with this D is better managed. Now that we understand the potential in the idea of double sparsity, let's discuss the training algorithm for it. This objective defines the learning process. We have a set of training examples, Yj, and we search for both the sparse matrix Z and the representations alpha j so as to get the smallest average representation error, while keeping both the alphas and the columns of Z sparse. As before, we could suggest a k-means-like algorithm. We start with an initial Z and iterate, jumping from a pursuit that updates the alphas and a dictionary update in which we update the matrix Z. We will imitate the KSVD approach in updating these columns one by one. Now let's dive into the steps of this algorithm. In the pursuit stage, we consider that D0 and Z are known, and thus the overall dictionary D is known. Seeking the alphas, we get a set of separated classic pursuit problems, and we have the freedom to choose any of the algorithms we are familiar with. Indeed, in the pursuit, we could exploit the structure of D to speed up the overall computations. The dictionary update stage is slightly more involved. We fix all the representations held in one big matrix A, and we aim to update Z one column at a time. As we have already said, we hope to imitate the KSVD approach, and this means that alongside with the update of a column in Z, we will also update the coefficients in A multiplying it. Here is our task, in which Z is the unknown. Writing the Frobenius part again, Z times A can be broken into a sum of the columns in Z multiplying the rows in A. Let's break this sum in order to isolate the appearance of Z1, which we will update. This is the first column in Z. Graphically, this is how this expression looks like, and we focus now on the first column in Z and the corresponding row in A. As in the KSVD, we have an issue with the first row of A, since it contains many zeros that should not be modified. We handle this matter by allowing only the examples using Z1 to participate in the update of Z1. Graphically, if this is the full expression for the representation error, then we remove all the columns from both Y and A that refer to examples not using Z1. Now, the first row in A is full, and we denote it as A1 tilde. And now to the actual update. We compute the error matrix E1, and our goal now is to find Z1 and A1 tilde to minimize this expression. E1 is the residual matrix that takes into account all the other atoms in D while omitting the first. We solve the resulting problem iteratively by fixing Z1 and updating A1 tilde. This is a simple least squares. We proceed by fixing A1 tilde and updating Z1. While this looks like a sparse coding problem, it is a bit strange since Z1 is multiplied from the left and the right. We'll come back to this. Iterating few times between these two steps leads to the desired update. Now let's zoom in on the update of Z1. The fact that our unknown is multiplied from the left and the right complicates our efforts. One very natural way to go is to change the order of the multiplications by relying on the Kronecker product properties. The problem with this idea is that the matrix multiplying Z1 now is huge and almost impossible to work with. A much easier and completely equivalent alternative was discovered by Ron Rubinstein as described here. The sizes involved now are very low, and solving for Z1 could be easily done by OMP or basis pursuit. So in this double sparsity algorithm, both the pursuit stage and the dictionary update stage apply pursuit. We now summarize. Double sparsity, as suggested in 2008, describes the dictionary D as the multiplication of a given transform D0 by a sparse matrix Z. The original work presented this rationale and the core ideas in how to turn it into a practical training algorithm. This work focused on the choice of a 2D or 3D DCT as D0 in its experiments. A follow-up work by Sulam and others in 2016 extended this work in several ways, offering what they call the trainlets. This double sparsity scheme used separable wavelet and an online learning, enabling this algorithm to operate on much bigger images, such as 100 by 100 pixels, while still being reasonable and effective. Another extension worth mentioning is the one by Gribonval and his students, who extended the above concept to a chain of multiplications of sparse matrices. This lovely idea could lead to an effective decomposition of given transforms, such as butterflies in FFT.